Hi, my name is Suman. I am an assistant professor in the mathematics department. So today we will going to learn this very important topic, that is mathematical induction. Okay, so when we apply mathematical induction, suppose we have a statement which depends on natural number. For example, let's take this question. So here the question is to prove that n square plus n is an even integer for all n belongs to natural number. That means if we take n equals to some natural number, for example n equals to 1, then n square plus n is 2, that is even integer. Similarly, if I take n equals to 2, then n square plus n is 2 square, that is 4, plus 2, that is and the summation is 6, that is also an even integer. Okay, so now to prove this statement we will use mathematical induction. Okay, so first of all, so let us define Pn be the following statement. Okay, so that is n square plus n is an even integer. Okay, now note that I use something p in the first bracket n. So that means my statement, the statement is this: n square plus n is an even integer. This statement depends on the values of n. So that's why we have written like this. So this statement is a function of n. Okay. Now if we can show that this statement Pn is true for all n belongs to natural number set, then we are done. Okay. So yeah. Next we will going to prove that this statement is true for all n belongs to natural number. Okay, so we will going to show that Pn is true for all n belongs to natural number. Okay. Now comes the mathematical induction. Okay. Yeah. First of all, if I take this step. So we will first prove this statement for n equals to 1, and that step is called base step. So base step is for n equals to 1. Okay. So now what is P1? P1 is 1 square plus 1 is an even integer. Correct? So this is the statement. Now what is 1 square plus 1? 1 square plus 1 is what? 2, which is indeed an even integer. So that means hence P1 is true. Very simple. So this is the base step. Now comes the inductive step. Inductive. So in this step we will let that Pn is true. Okay, so let Pm is true. Okay, then we will going to show that, so letting Pm be true, we will going to show that Pm plus 1 is also true. Okay, so this is the inductive step. So we have laid that Pm is true. Now Pm is true means Pm is true means m square plus m is even. Okay, and let m square plus m so this is m, yeah, m equals to sum 2p, because even number can be written as 2 into some integer, where for some p belongs to natural number. Okay, yeah. Now what is Pm plus 1? We have to show that m plus 1 square plus m plus 1 is also even. Now let's see. So this is m square plus 2m plus 1. Okay, and this is m plus 1. Now after some manipulation, so this is m square plus m plus 2m plus 2. Okay, now we already know that m square plus m is 2p. Okay, so this is from say start. So this is true because we have let Pm be true. Okay, now what is this? You can take 2 common and this is come out to be this. So that means m plus 1 square plus m plus 1 is also multiple of 2, which is equivalent to saying that this is an even integer. Hence m plus 1 plus m plus 1 square plus m plus 1 is an even integer. Okay, and this implies P m plus 1 is also true. So letting Pm be true, we have shown that Pm plus 1 is also true. So this is the inductive step, and from the base step and inductive step we can conclude that Pn, which is n square plus n is an even integer, is true for all m belongs to natural. That's it.